Well, welcome back, everyone, to our not even final session. So we're going to have a keynote speech now, then some more contributed talks, and then a panel discussion after that. And then after that, we're all going to go to the bar at Holland Hall and get pissed in the sunshine. So between now and, we'll indulge in networking and non-alcoholic beverages. That's all. So I'm really pleased to welcome Anne Jones. So I've been working with Anne a little bit for the last couple of years. It's been a really great collaboration. I don't think she's going to talk about that because she's got cooler stuff to talk about. So Anne works for IBM Research, where she's part of the Climate and Sustainability Group. They have done some foundational work on foundation models. So I think we're going to hear about Prithvi and a new one called TerraMind.
TerraMind, yeah.
So looking forward to that. And if you're interested in what she says, which I'm sure you will be, tomorrow there's a training session in the afternoon. I think there are still some spaces if you want to sign up. And I think that's a really great opportunity to learn how to actually do the things that she's going to inspire us with. Now, so over to you, Anne.
Thanks, Hal.
Enjoy your talk.
Hi, everyone. So yeah, it's very nice to be back in Exeter to give you an update on the foundation model work that we've been doing over the past year. I work with a global team in IBM Research, so I'd just quickly like to acknowledge my colleagues. So we have a team in Zurich who did the hands-on development of one of these models. We also have a team in Brazil that worked on the models. And Paolo Vaccaro, who couldn't be here today, unfortunately, from the UK team, is the overall lead of this work. So I'm sure many of you are familiar with foundation models, but just a quick reminder or a quick introduction. So what we mean by foundation models are a new type of AI which differs from traditional machine learning. So where traditional machine learning would train a model that in a supervised way for a specific task, the idea with foundation models is we have two phases. So we start off by training a large model on a large data set, and we do this in a self-supervised way. So that means that the training in that phase isn't dependent on any labeled data. And the way that we do this, so in our group we've been focusing on taking this approach and applying it to geospatial data. So the way that we do this pre-training phase for our models is by masking out parts of the data and then training the model to reconstruct it. And by doing this, we can then learn a general representation of the data in an encoder. And then, so this is through the pretext task. And then we take that foundation model that's in the encoder and we move to the second phase, which is fine-tuning. So we then do machine learning in a traditional way, where we take our label data, we add different decoders depending on the task that we want to do, whether it's segmentation, classification, regression, and we train that in a fine-tuning phase on the data. And this step is much more lightweight, so you need a lot of GPUs for the pre-training step, but in this fine-tuning step, we just need maybe one GPU. So the idea is that it's faster and cheaper to use the pre-trained models to develop new machine learning applications. We can increase the accuracy of the models, and we can make better use of the precious labeled data to achieve the model that we want to train. So, and one final point I want to make here was, in the geospatial domain, what we find is that to get the best accuracy for our application, when we do this fine-tuning phase, we allow the full model to be trained. So we don't freeze the encoder, we allow it to continue to be trained. And that's the way that we get the highest accuracy, and that will be important later on. Okay, so in IBM Research, as Hal mentioned, we have two threads of work in geospatial foundation models. So the first one, called Prithvi, is a model that we've been developing with NASA. So we've been doing that work for a few years now. This model is pre-trained on HLS data, so that's harmonized Landsat Sentinel-2, 30-meter resolution. And we have a second version of that model was released in December last year. And then more recently, we've been working with the European Space Agency on a model called Terramine, and this is a multimodal model. That's 10-meter resolution, and that was released in April. So what I'm going to do for the rest of this presentation is talk in more detail about both of those models. They're both open source, they're available on Hugging Face, and we also have a toolkit called TerraTorch for foundation model fine-tuning, so you can access them via that Python library. And so we're interested in taking this foundation model approach to build models which can address various environmental type applications. So now I'll go on to talk about Prithvi. Prithvi is a vision transformer-based model, and this second version has a number of improvements over the first version of the model that was released a couple of years ago. So it's trained on more data. It's trained on global data, whereas the first version of the model was just trained on the US. It actually has there's four different versions of the model. So there's 2 different sizes in terms of the number of parameters, and there's also versions that have temporal and location embeddings. So this allows you to put in extra context, which might help with specific tasks. So for example, if you want to do something like crop classification, you might want to feed the model multiple time steps, looking at winter and summer, for example, because that could help with your classification task. And these features were added by working with subject matter experts within NASA who were involved in the development of the model, so they could give some feedback on this model design. So the other big piece of work that's been done by the team working on Prithvi is on benchmarking, which I'll talk about next. So as we started working on this second version of the model, we felt it was really important to be able to compare Prithvi to the whole range of foundation models that were emerging. This is a very fast-moving field, which is why we got involved in GeoBench. So this is a benchmarking framework. It consists of some data sets, so some classification and segmentation data sets, and it also provides a protocol for fine-tuning models. So this means that you can follow that recipe, and it gives you a way to fairly and reproducibly compare different foundation models. So for example, there's a certain amount of hyperparameter optimization that you're allowed to do. And so we've been working on that, and there will be a new version released later this year with more data sets. And you can see the diversity of tasks that are represented in that benchmark, in those benchmark data. Also, as part of doing that benchmarking, we needed to do the comparison to other foundation models. So we've actually added at least 10 other foundation models are actually now available in TerraTorch. So if you use that package, you don't have to just use IBM models. You can evaluate all these models and see which are the best for your task. And just the table here gives you an indication of the variation that you get across different foundation models that are available now. So you have different architectures, different sizes, different ways of pre-training, different pre-training data, different resolutions. So there's a range, and the question is, which one do I use? Which one do I use for my task? And the aim with this benchmarking is just to give a first indication of the performance, and then that could tell you, if you consider a particular application, how did that model perform on similar tasks in the benchmark. In terms of overall Prithvi 2 performance, we're very happy to find out that Prithvi 2 did outperform the other models. So these were the models that were chosen based on the previous work with GeoBench. So Prithvi did overall on those tasks outperform the other foundation models. It was 8% better than Prithvi 1, I believe. The performance on classification was really quite similar across the top models. Prithvi didn't come out top for classification. The top model is DOFA, which has been pre-trained on high-resolution data, which probably gave it the edge. But then Prithvi performed very well on segmentation tasks. Right, so that was a quick tour of Prithvi. So our other model that we've been working on with European Space Agency is called TerraMind. This is the first generative geospatial foundation model. I'll talk about that more in a minute. But there's a striking feature about it is that it ingests and has been pre-trained on multiple modalities. And I know there's some kind of, there might not be agreement about what modalities are, because in this sense, in this model, what we're talking about is different types of geospatial data. Right? So we have Sentinel-1, we have Sentinel-2, we have elevation, and we have these derived modalities, so land use, land cover, and NDVI, which are derived from Sentinel-2. So this was inspired by a model called 4M, which was trained on text and image, and the idea was to take the same sort of approach to geospatial data. And by including these derived modalities, it's trying to teach the model a bit more about the sort of context of what we're interested in for our type of applications. And we'll see in a minute how that can actually help with our fine-tuning tasks. So the model was trained on this data set called TerraMesh, which consists of aligned samples across all those modalities, and that will be released later this year. There's already a paper on that, if you're interested. So the architecture of TerraMind is quite complicated, and if you'd like to read more about it, we do have a preprint paper, so I'll just highlight a few details about it. So the idea was to take an approach at how do you efficiently train a model across all these modalities. So what we've done is, first of all, we train tokenizers on each of the separate modalities. So this is done for the image-based modalities using diffusion models. And here we get like a compressed representation in tokens of each of those modalities, and it compresses the data by up to a factor of 3,000. And then once we've got the tokens, then we do the same sort of masked reconstruction that we do for Prithvi. But this time, the model is trained to reconstruct across modalities. So you mask out some modalities, and you mask out other modalities in different places, and you use the model to reconstruct. And by doing this, it then means that the model can actually generate missing modalities. So the way that works, so what we can do is, for any of those modalities, we can use it to generate any other modality. So if you look in the top line here, you're providing Sentinel-2, excuse me, you're providing Sentinel-2, and then the model is generating what it thinks the Sentinel-1 image, the DEM, land use, land cover, and NDVI look like, based on that image. And you can see that with Sentinel-2, it can do quite a good job. If you only give it elevation, you can see that it gets the coastline, but it's not getting any of the interior detail. So what we really want to do, of course, is actually fine-tune the model for specific tasks and do this with multiple modalities of data. So the evaluation of this model was done on a different benchmark, so GeoBench is not the only benchmark. Pangea is another benchmark that was developed by the European Space Agency. So they did the evaluation of TerraMind on this data set. So this consists of 9 different segmentation tasks, and 3 of them are multimodal with S1 and S2. So again, on average, so we had 2 versions of TerraMind. In fact, there's a large version and a smaller version. So on average, across these tasks, TerraMind did outperform the other foundation models that are included in the previous Pangea paper. And one thing about this Pangea benchmark is it's different in terms of the protocol. So it actually specifies that the foundation model encoder has to be frozen. It's not allowed to be tuned during the fine-tuning process. So that's kind of much stricter on the foundation models, like really investigating how well they've represented the data. But then that makes it quite difficult if you want to try and use it for a task that uses different data to the pre-training data. So what we found is that for the first time, TerraMind was able to outperform a fully fine-tuned UNet in this setup. So normally, if you freeze the encoder on these geospatial foundation models, they can't do better than a UNet that you can fully fine-tune, but TerraMind was able to do that this time. If we look at the other type of tasks, so where we have tasks which match in terms of input modalities, the model does very well. Where we have tasks like this burn scars one that uses HLS data, Prithvi, the first Prithvi model actually outperformed TerraMind because it was pre-trained on the HLS data. And then finally, the task on the right there is a high-resolution task. So again, that's very challenging under this setup. So we also evaluated for those 3 tasks that had Sentinel-1 and Sentinel-2 data available, that the model did improve its performance by including both modalities over just using one or the other. So these tasks are 2 agriculture-type tasks, identifying agricultural areas, and a flood detection task is the middle one. And then finally, we have this really interesting feature of TerraMind. So this was inspired by the fact that the model can generate missing modalities. So we have this mode of fine-tuning called thinking in modalities. And this is where, during the fine-tuning process, you ask the model to generate tokens for one of the missing modalities. And you actually use that as an additional input to your model. So it's sort of getting the model to think about what might be relevant for a particular task. So in this case, for flood detection, generating land use, land cover internally, even though it's not an input, seems to help the model perform better because it knows where the permanent water is, where the land is, so it can actually then better detect flooded areas. And it also helped with crop type segmentation as well, generating the land cover, sort of steering the model towards land use information that's relevant to the task. So we see in the statistics, you see that you get a modest improvement in scores from having this version with thinking in modalities. But then when we were looking at examples, we found in some situations it's actually quite striking, the effect. So I've got an example here. So this is looking at ship detection. So this is the MADOS data set that I showed earlier. So we're here in New York Harbor looking at detecting ships. And this example shows the detection using TerraMind using only Sentinel-2 data without any extra features. So you can see that we detect some of the ships, but we're missing quite a lot of them as well. And then if we take the thinking and modalities version, now we zoom out, we're going to generate land use, land cover. So we've got the built-up areas, we've got the water, and then we use that as part of the fine-tuning for ship detection. And then you can see it really detects a lot more ships. So we knew that the model did well on this data set, but we're quite surprised to see there's actually a really big impact of using that extra modality. And here you see the potential use case of this model in monitoring shipping activity. So here we're just aggregating up the ships detected in each location and then tracking it over time. So this is a time series for different harbors in the US over Q1 2025, where you can see LA is the busiest harbor. Okay. So a few conclusions of this. I hope I've illustrated how Earth observation foundation models are increasing in sophistication, increasing in performance, and then we're also trying to continue to make them accessible, both in terms of having the tools so that you can interact with the models and try them out, and also using the information from benchmarks so you can sort of guide your choice. So there's a lot of focus in the AI community on benchmarking and those statistics, but what you realize when you look at them is that that's only the beginning. And if you want to find out the real value of these foundation models, you have to use them in real-world applications. So that's what we want people to do now, is actually get your hands on them and try them out. And what we're looking for is not like a few percent improvement in performance. We're trying to find what are the applications that we couldn't do before that we can do with these models. Perhaps there's applications where you don't have enough data to train a model. Can the foundation model help you do that application? Some things that are coming next. So we are interested in adding further modalities to TerraMind. So weather data. There was some text used in pre-training TerraMind, but only in a very limited way. So it would be very interesting to make that more sophisticated. I think as we've seen over the past couple of days, we have a lot of use cases that use high-resolution data. So in the benchmarking, we did use both models on tasks that actually did involve higher resolution, like 1 meter resolution data. But we're interested in looking at how we can do some pre-training on high-resolution data to make the model even more powerful. And then finally, adding a time dimension. So Prithvi has this ability to add in multiple time steps. Currently, TerraMind is just a single snapshot. But when we're thinking about the future and where these foundation models are going, a lot of the questions and a lot of the value, I think, is about things like making predictions and understanding risk. So for that, to introduce that capability, we really need to bring in some sort of sense of time and bringing in physical processes as well. So that's a really interesting area to explore. So a couple of promos. So there's a challenge currently ongoing around TerraMind, which you can win real money for an application. So please check that out. And if you want to learn how to do it, we have this session tomorrow where Jeffrey and Rosie will take you through a couple of examples. So we have one Prithvi example and one TerraMind example. So you'll see how you can use both models with TerraTorch. And then you can explore all of the possibilities with that and, of course, try out other foundation models as well, which are available in there. And that's everything from me.
Okay, fantastic. Thank you, Anne. So we have a few minutes for questions, if anybody would like to ask. Gentleman at the back in the green shirt. Yes, you? Yeah.
So do you provide the fine-tuning toolbox, or does the user have to write their own? And what kind of method of fine-tuning is compatible with your model?
Yeah, so you can use TerraTorch to do fine-tuning, and you can do segmentation, classification, object detection, and regression using that with any of the foundation models that are available, that are onboarded. So you need to prepare your data. That's the main thing that you need to do, and then the toolkit will help you do the fine-tuning.
So just to follow up, does it mean the method of fine-tuning is fixed in the TerraTorch?
Well, there's various different options of like architectures that you can add on. But if there's a particular method that you want to use, perhaps we could talk about it, or if you can join the session tomorrow, you can go through it.
At that moment, can you just say how people sign up for the workshop if they want to come?
8. 8 people are left to sign up.
Eight people can sign up.
And there
Of now.
No, there's only 2 spots left, I'm sorry.
2 spots, okay, they're going fast.
They're flying in.
Is it via the website for ML4EO?
There's a form that you would have received through some of the communications, but if you go to scan for the program and you click workshops, the form link is on that top, so there's 2 spots remaining now.
It's worth turning up even if it's full. Somebody might not make it. Very patient. Okay, another question, please. Yes.
Yes, I had so the first was, could you comment on the difference in GPU hours used in Prithvi versus Terramine? Because there's a fair big difference. The second was, could you explain a bit more about the correlation learning phase of Terramine?
Okay. So Prithvi is a bigger model, so it was trained for longer. Terramind is smaller, which is why even though it uses more data, it's a smaller model, which is why the training time is less. So it's trying to be more efficient. But I think that GPU hours doesn't include training the tokenizers, so that's just for the actual correlation learning. And then in terms of this correlation learning part, I may be pointing to the paper to get all the details of it. I don't know if you have a specific question about exactly how it works, but it's essentially just learning to reconstruct across modalities. So we use both tokens and we use pixels as input so that we keep the fine scale detail. And then we mask tokens in the target and in the input, and then we train the model to predict the missing tokens across multiple modalities.
Do you do that with the text tokens too?
No, it's just we're just. Yeah, I think they did do it with the text tokens. Yeah, I'm not 100% sure about the text because that's not been a big feature of it, but they do it with location, so it can predict locations. Given that's another modality it can predict. Given images, but I don't think with the text it can do that. Yeah, we'd have to check on that.
Okay, we've got time for one more question, and while that's happening, where's Remy? He's giving them one down and just start prepping yourself. Who would like to ask another question? Karen.
Thanks for the interesting talk. I was just wondering, beyond the sort of recreation of the spatial image sets, which are quite impressive in some of these cases, how does it do on the radiometric pixel values? So, if you were to sort of look at the products of this and delve into the backscatter or that's predicted, or the reflectance or whatever, how well does it perform in terms of recreating those?
For the generation?
Yeah.
Yeah, so I would say on the whole that the generated images are far from perfect. So if you compare the generation with the truth, it won't even match. But the aim is to just use that information for the fine-tuning rather than actually be able to completely recreate the images. So I guess that would require further refinement for that specific purpose.
Yeah. Okay, thank you.
All right. Well, thank you very much, Anne. Thank you for a wonderful talk. We'll be around for the evening if anyone wants to ask you more questions.